So I organized several conferences. Actually, I was president of this KSCM, Korean Society for Composite Materials, until 2024, the end of the December. So this KSCM was founded in 1987 as a scientific engineering and professional organization. It has more than 5,000 members, 5,000 members. I also organized this kind of international conference, ACCM 13, every 2 years. Last year was held in Kyoto, Japan. At that time, more than 300 participants were there. So at that time, I made a plenary speech there. Can you find me here? Here. I was here. Yeah. And this is steering committee members from Australia and Japan and Hong Kong and China and Korea. This is a steering committee member from South Korea. This is also, I am organizing in Vietnam, MMMS. Okay. This is from Japan, AMDP, Advanced Material Development and Performance Conference, every 3 years. From now, I'd like to introduce our university briefly, located in southeastern tip of Korean Peninsula. Busan is the second largest city in Korea. It will take us 3 minutes, just look.
This is Korea Maritime and Ocean University. The Republic of Korea has infinite possibilities to grow as a maritime country. The driver that will lead Korea to become a great maritime power for more than 70 years. At the center was the Korea Maritime and Ocean University. The Korea Maritime and Ocean University has various maritime specialized and advanced facilities and equipment to cultivate experts in the maritime field, including the Han-Bada-ho ship and Han-Nada-ho ship, for providing hands-on learning for advanced marine technicians. Skilled maritime personnel are cultivated through the Marine Simulation Center that enables simulation training related to ships. Also, there is the VR room that can show ultra-large offshore plant structures in 3D video. The Industry and Application ETRS Center, where various new technologies and advanced teaching methods are employed, and other town facilities are used to conduct maritime education and research. Moreover, students can freely take part in discussions and learning in a cafe-type learning area. Thanks to the effort and training of maritime personnel, the Korean Maritime and Ocean University leading maritime education, research, policy, and culture in the Republic of Korea, and the university developing into a maritime specialized, comprehensive university recognized the world over. Beyond the sea, the Korea Maritime and Ocean University encompasses a bigger world. The school manages specialized education and research for all fields, including the traditional maritime fields of ocean transport, shipbuilding, ports, and distribution, but also also the fields of ocean engineering, ocean science, marine finance, and ocean leisure. Further, in step with the fourth industrial revolution, the school is leading the future maritime industry with autonomous navigation, smart ships, and maritime future cities. The comprehensive university with a global maritime specialization of the highest international standards. This is the Korea Maritime and Ocean University. Methodical maritime personnel are cultivated at 3 colleges: the College of Maritime Sciences, the College of Ocean Science and Engineering, and the College of Humanities and Social Sciences, and at 5 graduate schools: the Graduate School of General Studies, the Ocean Science and Technology School, the Graduate School of Maritime Industries, the Graduate School of Maritime Finance, the Graduate School of Global Logistics.
산민이 바다인 이 땅에서 해양 산업은 우리나라의 과거이자 현재이고 미래입니다. K해양의 미래, 국립한국해양대학교가 세계로 가는 키가 되어드리겠습니다. 국립한국해양대학교와 함께 하시기 바랍니다.
A vast sea. We are not afraid to venture out beyond Korea into the world. The Korea Maritime and Ocean University will be the compass and our dependable companion on the voyage of our life.
Our university is established firstly as a national university in Korea. Actually, it was established in 1919. And from now, I'd like to introduce about our composite lab. Here, me, and I have 2 postdocs from India. Right now, from Sanjay Kumar, is very smart, and he has really good ability to publish many papers. And I have also doctoral candidates from China, and also Kenya, and Pakistan, and from Korea. And also I am collaborating with several institutes in Korea. They are all my ex-students. So let's enjoy. I'd like to introduce about my ongoing research. This is closely related with Korean Air. So I'd like to introduce briefly. This is included some kind of a secret factor because it is closely related with industry. Please to remind ongoing research. Here, this is my first project from our government. Development of a partial structure for the entrance wall based on the thermoplastic composite materials in a single passage class aircraft. I am now collaborating with Korean Air and Airbus and so many institutes like this. Korean Air and Songwall Technology and ANH Structure and KITEC, several institutes were included in this project, consortium project. As you know, our composite material is widely used in aircraft and automotive and ocean industry, shipbuilding. So very important nowadays, especially in aircraft. Aircraft is used more than 50%. So our final target will be like this. Every day we evaluate and we apply. like a stiffener and skin by using the oven consolidation system, like this, and the skin, stiffener consolidation system. And the second one, the development of a skin spar integrated wingtip. Yeah, this project was done during 5 years. So all those results from 5 years research. Here's our background. And manufacturing process is like this. And AFP and the high temperature RTM process, resin transfer molding system we are using. And our final end product will be like this, wingtip full scale. And another one is aircraft structure based on thermoplastic carbon composite. So as you can see here, my project is closely related with mechanical engineering and material science and nanomaterials. So you can see all those fields. Our background is like this. We are now trying to develop this kind of cargo door. And our end product will be like this. The procedure will be like this. The seventh, optimization of interleaved structure with amorphous. Finally, I will conclude this systematic research. Okay? Here is my research flow chart. First, we have to know the basic mechanical property. So it is the first one. And open-hole properties are crucial for composite structure because open holes are often required for joining application. And pin joint properties are essential for the joining of a composite structure. Voltage joint properties is also very important for composite structure. And adhesive joint properties are essential for the joining of a composite structure. As you may know, the composite material is very serious problem due to the delamination problem. So here, basic properties are necessary to restrict the delamination that occurs at open hole joint, pin joint, and voltage joint. Also, we have to apply this kind of composite structure to industry, like the aerospace and automotive and shipping. So, industrial purpose composite structure very important to develop. So, I'd like to present the first topic. Combined effect of temperature and preventing on the fracture properties of carbon fiber polyethylene composites. So from now, let's enjoy. Okay? So that is here. As you can see here, fiber reinforced thermoplastic polymer FRTP is widely used in this aircraft, and also UAM structure, also automotive. We are now targeting to apply in this structure. So the classification of plastics is like this. Amorphous structure as a super engineering plastic. This and engineering plastics is like this. And also as a semi-crystalline here, I'm now using this kind of pack, shape pack. So just to remind this. In aviation, the cruising altitude will be 9 to 12 kilometers, right? And the temperature is minus 40 to minus 7. So our temperature range will be minus 196 Celsius as a crucial temperature, critical temperature. And also minus 60. And our shape pack is the crest transition temperature is 159. 159. So we decide the temperature 140 and 200. This is our temperature range for experiment. We prepare the specimens like this. The shape pack composites are fabricated with 12 layers of pre-prep and consolidated under vacuum and achieve a thickness of 1.7 millimeter and an exceptionally low we have to lay. The procedure is like this. We stack the pre-stack 12 stacked layers shape pack, and by using the vacuum bag, and we use the oven consolidation. After that, we prepare the finally composite plane. As an experimenter, preventing is very important. So, prevent three trial at the room temperature identified 30% and 50% prevent as below, and 70%. Same images show distinct reflective pattern, indicating more brittle behavior and also tensile property and the failure behavior of a shape pack at different temperature. Stress strain curve, also the temperature range and the fracture pattern. In case of room temperature, the fracture pattern is like this: low temperature and extreme cryogenic temperature. So this slide means tensile tests show the shape pack, the Young's modulus and the strength increased with decreasing temperature due to reduced polymer chain mobility, enhancing rigidity. At the lower temperatures, improved fiber matrix bonding and reduced ductility resulted in higher tensile strength and more brittle fracture. This kind of result published in composite part A. The impact factor is more than 7. A very good journal. So this slide shows the fracture stress and strength relationship. And as you can see here, the temperature decreases. The temperature decreases. Extreme cryogenic temperature decreases. Shape pack composite exhibit increased fracture strength. More increased and toughness due to the enhanced matrix rigidity. Transitioning from compressive to tensile failure mode, thus improving overall low temperature performance and damage resistance. Just look at this mechanism. Thermal stress will be occurred like this. In case of fiber, under compression, and matrix under tension. This kind of residual stress will be occurred here. The fracture mode will be changed. This slide shows the effect of prevent on fracture behavior of shape pad. As you can see in this figure, increasing preventing leads to reduced fracture properties in shape pad composite with a significant decline in modulus and strength as prevent approaches and exceeds the material's yield point, causing extensive micro-cracking and debonding. Under 30% prevent and 70% prevent, you can compare. In case of 30%, like this, and in case of 70%, cannot be reverted to the original point. The pattern is very different. We also observed the fracture morphology. Also, effect of temperature on fracture behavior of prevent shape pad. You can compare in case of 30% prevent. The fracture morphology like this. Just look at the procedure. Temperature and preventing significantly affect shape pad fracture properties at the low and extremely low temperature, while modulus changes are minimal. Strength and strain increase, highlighting shape pad's resilience, but also revealing increased matrix cracking and reduced post-yield modulus. Just look at the fracture morphology. Can you follow me? Yeah. Let's go slowly. And this slide shows the effect of temperature on the fracture behavior of prevent shape pad. In case of 70%, big difference. Low temperature, extreme cryogenic temperature. The micro cracks will be occurred like this. Micro cracks. Low temperature, extreme cryogenic temperature. Micro cracks will be occurred like this. So you can compare between 30% and 70%. This slide shows the residual flexion strength. Room temperature, extreme cryogenic temperature, and low temperature. Residual flexion strength in shape pad decreased with increasing prevent intensity, but 30% prevent specimens retain the highest strength at all temperatures. Here, 30%. Highlighting their durability for demanding aerospace application. This is a very important result. So under 30% prevent, we can use. This is very important result. So the our consortium is using this data. I'd like to move to the second issue. Tensile behavior of open hole and pinned joint and bolted joint of a shape pack composite under extreme temperature. Mechanical joints offers several advantages, like easy installation, repair, and resistance to environmental factors, and higher safety factor, reliable and preferred joining method in modern composite structures. But when we create a hole, the stress concentration will be occur like this. It will reduce the life of composite. So you can see this kind of shader. So at this point, it is very important to check the joint efficiency. The joint efficiency here. Joint strength influenced by joint geometry. Width to hole diameter, W/D ratio is very important here as a parameter. And edge distance to hole diameter, E/D ratio is very important. So in this paper, very important factor is W/D and E/D ratio. So the systematic research will be performed. We use the shape pack prepreg provided by Solvay company. And as a specimen preparation, the procedure is like this, and we use the oven consolidation. We prepared 4 kinds of specimen. Here, as an experimenter, unnotched tensile specimen based on the ASTM D3009. The second, open hole specimen prepared based on ASTM method, and the pinned joint also based on ASTM method, and the bolted joint based on ASTM method. We prepared 4 kinds of specimens like this: unnotched specimen, and open hole, and pinned joint, and bolted joint. Here we are copying with some limitation, because this is a very, very expensive material. 1 roll, the price will be $10,000. Very expensive material. So it is not easy to handle this material. So we have to be careful. We have to be careful to handle this kind of material. Really, very expensive. So we have to be careful to prepare this kind of specimen. First result, tensile properties and the failure behavior of open hole shape pack at different temperatures. Please look at this data. This is from the reference value. Composite, carbon epoxy, aspiglass epoxy, and carbon epoxy. Just look at the strength retention value, around 45 to 52%. But our shape pack composite the strength retention reached to the 69%. This means this is very good, high quality material. So we are using this material. This slide shows the tensile properties and the failure behavior at a different temperature. Also, we published in Composite Part A journal. We changed the W by D ratio 4 to 1.5, 1.5 to 4. So just compare those behavior. In case of 1.5, the behavior is like this, small strain, and 2, 3, 4, at low temperature and high temperature. The fractional morphology is like this, will be changed like this. The failure behavior of pinned joint at different temperatures, W by D effect under constant E by D ratio equal 4. Just compare the result. We prepared this kind of specimen. The result is like this. In case of W by D equal 1.5, low temperature, room temperature, high temperature. Low temperature and high temperature showed decreased peak load with different trend in stiffness and displacement, right? Just look at the flex behavior. In case of 1.5, totally occurred detention hold. In case of 2, can you see the bearing failure mode? Not the detention. Called bearing error. This is the result, 3 and 4. Whole bearing failure. Bearing. W by the 3 and 4. So, finally, we summarize like this. W by the effect under constant E by the ratio equal 4. Marginal load increased due to the same bearing failure. Increased specimen width prevented detention failure move. Bearing failure achieved beyond W by D ratio 1.5. Very important result. Just compare low temperature, high temperature, same W by D ratio. The flex will be occurred like this as a bearing mode. And pin joint shape pack at different failure temperature, the flex behavior, geometry effect at different temperature, E by D ratio effect. Just before we compared the W by D ratio. This is E by D ratio under W by D ratio, the constant ratio. Okay. So increasing E by D ratio shows a slight increase in the peak load. Just compare the peak load under the different temperature range. You can compare also the flex morphology pattern Very similar. Very similar. Just we'd like to compare the bearing strength. Bearing strength between bearing strength and the W/D ratio shows right there. Bearing strength primarily influenced by W/D ratio, right? And E/D ratio had minimal impact. Also, bearing strength at the low temperature and the high temperature slightly lower than room temperature. W/D ratio and D/D ratio equal to 4 shows the highest bearing strength. Right. This is also a very important result as a bearing strength. Let's compare with the reference value. Carbon approach. Carbon approach, carbon approach. The stacking sequence is like this. Move on, and the sequence is like this. The bearing strength, the value is like this. Just look at the value. Almost from 160 to 370 range. Right? So, here, our shape path reach 428 megapascal as a bearing strength. Very, very high level. Just the people 160 to 370, right? But here, 428 megapascal. So it means not worse level of bearing strength. So we are use this material. Tensile property and failure behavior of pinned joint at different temperature as failure behavior at the room temperature. W/D effect 1.5 net tension. To practice morphology is right there. Just compare. In case of W/D equal 2, we observe here the fracture morphology is like this. Buckling and kinking and kink collapse and bending failure and shear shape crack and shear driven compressive. So we can observe the intralaminar crack and interlaminar crack. We can observe here. Very important result. So complete bearing failure was achieved as the W/D ratio increased to 2 and beyond. As the load increases, the matrix undergoes plastic deformation, leading to fiber buckling and increased specimen thickness and eventual failure. Fiber kinking causes the bending failure in the 90-degree lamina, promoting the shear-driven compressive failure. So, just before we compare the result, W/D ratio, from now, E/D ratio, under constant W/D ratio. E/D ratio equal 1.5. Intralaminar crack caused by kinking in 0-degree propagated to the edge, contributing to the lower bearing strength. And the higher E/D ratio then 1.5. Intralaminar crack confined to the whole region. Due to large distance between the hole and the edge of the specimen. At the low temperature, we can observe the buckling and kinking and king collapse, bending failure, and the shear-shaped crack, shear-driven compression. So temperature changes, the thermal deformation occur along the 5 directions. Intralaminar crack and interlaminar crack also will be occur. At the low temperature, fiber under compression, matrix under tension. So the reduced thickness of specimen due to the temperature-induced acceleration of a localized compressive failure. At high temperature, we can observe the cracks pattern like this. At high temperature, increase the ductility, right? So increase the ductility of a PEC resulted in significant large plastic deformation and external phyllo you can observe. In this case, fiber under tension, matrix under matrix, right? So the severe bending failure in 90 degree due to the accelerated compressive failure of matrix. We check the situation by using the DIC. In case of 1.5, geometry effect, load displacement. DIC images at the 99% failure displacement reveal minor bearing before fracture with predominant tension failure. We check the situation. In case of 1.5, in case of 2, just compare the fracture pattern. Increasing W by D to yields 66% higher peak load and displacement. DIC images show increased bearing, shifting from net tension to combined net tension or bearing mode, with minor bending near the bolt contact area. This is W by D equals 3. DIC pattern like this. I will skip this, very similar with the previous slide. Just look at the fracture pattern, bearing area. Here, the fracture morphology. I'd like to change the temperature effect at the different W by D ratio, 1.5, 2, 3, 4. Just compare the result. Temperature influences the load bolt displacement. Low temperature enhances the stiffness and reducing displacement. High temperature degrades stiffness and increase ductility. Finally, we compare the joint efficiency depending on the W by D ratio. Just to look at the results. Because of time limitation, I'd like to move to the next issue. Here, strengthening of a composite through incorporation of a halloysite nanotube. From now, I'd like to move to the nanomaterials effect. This slide shows the left shear properties of shape pack composite through nanoparticle enhanced adhesive joint. We prepared the specimen like this. Schematic illustration of the preparation of PEI, HNT means halloysite nanotube, film for shape pack adhesive joint. We observe HNT dispersion situation. In case of 1% HNT and 3% HNT, we can observe the nanoparticle aggregation. This is a very big problem in cooperating to the composite material, because this kind of aggregation occurs stress concentration. But this is a big problem, so we have to solve it. So, in case of the this aggregation situation, two stages of aggregation will be occurred. First stage will be occurred by van der Waals force, and second, chemical shrinkage. So, two types will be occurred. So, 0.5 and 1.0 and 3%. The situation is like this. We check the thermal properties. Tg will be changed against the PEI 3% and 1%, 0.5, and PEI need. You can just look at the Tg. Check the VSC conditions and cross transition temperature. Also, we performed the left shear strength test through nanoparticle enhanced adhesive joint. The left shear strength for 0.5 HNT is the highest value shown. This is the main result here. Over 0.5 decrease. So we finally used this 0.5 result. Also, we observed the flex pattern, 0.513%. Detection of SI and the AR indicates the bonding joint interface is formed by the complex layer of PEC, PEI, and HNT. Situation is like this. PEI need, PEI plus 0.5 halloysite nanotube, flex morphology. We can observe several phenomena here. case of PEI, need shows smooth ductile drawing and exposed fiber and exhibits poor bonding between fiber and resin. 0.5 is the most important for the person. So 0.5 shows rougher ductile drawing with resin residue and custom morphology, indicates the improved interfacial bonding. In case of 1 and 3, just to look at the brachymorphose and compare. So, from now I'd like to move to another issue. Effect of melting fusion of PT, PEI, and P, thermoplastic film, interleaves on the flex toughness and film behavior of carbon, fiber, epoxy, thermosetting composite. This left-hand side shows the application of 5 reinforced composite. So, yeah, automotive and UAM and aircraft. We prepared the specimen like this. Just before I mentioned about the delamination. Delamination is a big problem. So we have to prevent this kind of delamination. We use the PET, PA, PEEK. We prepared CFTP, preform, and the stacking procedures, and we use the vacuum-assisted resin transfer molding. And finally, we prepared the mode 1 specimen and the mode 2 specimen. This is the result of mode 1. Again, the lead PET, PI, P. The situation is like this. In case of a PEI and P, we can observe fiber bridging, nano bridging occurs like this. But NEAT and PD, we cannot. We also observe the same image. NEAT, PD, PI, P. In case of mode 2, the result is like this. I will skip the details because of time limitation. Mode 2 result, same result, like this. This schematic representation of melt infused interleaves toughening mechanism. This result is published in Polymer Composites. Incorporating PET, PEI, and PEEK film significantly improved the mode 1 and the mode 2 ILFT interfacial flex toughness. And the failure modes in mode 1 were characterized by cohesively failure and predominant intermittent adhesive failure, leading to the tortuous crack path. with extensive plastic deformation in PI and PEEK interleaved laminate. In mode 2, the knit and PI laminate fail cohesively while in PEEK laminate, the crack deflected to the weaker TP epoxy interface resin due to its weaker bonding with epoxy than PI and limiting its full toughening potential. This result acknowledges the critical role of matrix compatibility. I'd like to move another issue. Optimization of interleaved structure with amorphous halloysite nanotubes for superior performance of shear-bonded pipes. In various environmental conditions, this is a very important thing in our case because we have to apply to the shipbuilding. As you may know, the halloysite nanotube by heat treatment, the microstructure will be changed, right? Over 700 and 1000. The structure from semi-crystalline to amorphous structure. Very important thing. The water layer will be disappeared. So we prepare the specimen, epoxy, nanotube. We prepare the specimen. In case of a pipe composite, we prepare the 5 kinds of specimen. E3 means this, knit epoxy. And E2A1 means 2 layers of knit epoxy and amorphous 1 layer. So we change. We designed like this, 5 kinds of specimen. The result, flat and cylindrical specimens were made using filament winding on a 400 millimeter mandrel. We call this mandrel. And filament winding. Finally, we can get the 5 composites. Here, heat treated at 80 Celsius for 5 hours. Amorphous halloysite nanotube reduce moisture absorption significantly, with amorphous structure achieving the highest reduction, 190. Here, interleaved structure with amorphous halloysite nanotubes for superior performance of shape RP pipes in various environmental conditions. This kind of all result also is published in Thin Walled Structure. Amorphous halloysite nanotubes significantly reduce the moisture diffusion. Very important thing. Due to their barrier properties, a tortuous barrier will be made, incorporating with the halloysite nanotube. Just to compare those results, fracture stress and strength. Before moisture absorption, after moisture absorption, after drying. The situation is like this. We can summarize it like this. Before moisture absorption, AHNT composites showed superior fracture modulus and strength. A3 had the highest strength, mean amorphous structure, 3 layer, showed the highest strength. Moisture reduced the fracture properties, but AHNT composite retained higher performance, with showing 30% reduction. Before, after drying, the situation is like this. Morphology change. Also, load and 5 diffraction. All those design structures change like this. This slide shows the relationship between 5 stiffness and before, after drying. The result is like this. So here, as you can see, the most highest value is A3, 0.5 halloysite nanotube, and amorphous halloysite nanotube is the most, showed the most highest value. We check the situation and the flex pattern. Finally, I'd like to conclude all our research result. The first, influence of W/D ratio and E/D ratios on bearing strength and failure mode. Geometry effect. Increasing the W/D ratio significantly enhances the load carrying capacity, with a notable transition from net tension to bearing failure mode beyond the W/D ratio of 1.5 E/D ratio. This is a very important thing regarding geometry effect. And the second, temperature-dependent mechanical properties. CF-PEC composites exhibit temperature-dependent mechanical behavior with lower bearing strength at high temperature compared to the room temperature and low temperature. The composites maintain good interfacial bonding without delamination across all temperatures, showing higher stiffness and lower displacement at low temperature and increased ductility at high temperature. This is the second result. And the third, impact of a nanotube reinforced on adhesive strength. Incorporating just 0.5 HNTs into the PEI adhesive in CF-PEC joints significantly improved LS left shear strength due to the enhanced interfacial bonding. However, highest HNT loadings lead to aggregation, reducing left shear strength. Regarding the effect of melt infusion polymers, melt infusion of PET, PI, and PEEK films into carbon fiber composites significantly enhances the flex toughness and the damage tolerance with improvement of up to 284% in mode 1 and 188% in mode 2. Interfacial interlaminar flex toughness, establishing it as an effective toughening technique. The fifth one is moisture absorption and mechanical performance. Carbon fiber composites modified with amorphous halloysite nanotube exhibit reduced moisture absorption and higher fracture and fiber stiffness, both before and after moisture exposure. The A3 and E2A1 structures partially demonstrate superior mechanical performance and the shoulder stiffness post moisture absorption, making them promising for industrial application. Final one. This is the final one. Comprehensive insights from our experiment research for design and optimization. The studies correctively highlight the critical role of geometric parameters, double biduration and biduration, temperature effect, and nanotube reinforcement in optimizing the performance of CFX composite. These factors should be tailored for high-end structural application, ensuring long-term durability and efficiency in challenging environments. So this is our systematical research. So I concluded finally the comprehensive insight. So thank you very much for your kind attention. This is my composite family. Yeah, here. From India, Sanjay Kumar, Dr. Sanjay Kumar, and from Kenya. We enjoyed the summer vacation in Korea. Yeah, that's it. Any question? Oh. Yep, regarding your very good question, regarding your question, one Korean company is trying to make that kind of hydrogen storage. My ex-student is working at the company. So nowadays, by using the filament winding method, they are trying to make that kind of hydrogen storage by using the thermostatic composite. No, yes, yes.
So how much it handle the pressure or temperature?
Yeah, at this moment I cannot say, but we can overcome that kind of limitation, I think. They are now developing. Yes. So next year, I will organize one international conference in Korea, Busan, AMDP and PEMMA conference, combined conference. So your participation will be highly appreciated. Okay. Maybe the end of the June next year, 2026. Okay. In Korea, Busan. Okay. See you again in Busan. Okay. Thank you so much.